Incredible. Behind the apps and services you use every single day. How do platforms handle millions of users, process just massive amounts of data, and still feel incredibly fast and responsive? Today, we are going to pull back the curtain and embark on a fascinating deep dive into system design.
Yeah, and what's truly captivating here is that we won't just talk in, like, abstractions. We're going to get very concrete. We'll be breaking down the foundational principles of building scalable, reliable systems by looking at four distinct and, incredibly popular real-world examples. Strava, distributed cash, GoPuff, and Robinhood will meticulously examine their unique functional needs, their crucial non-functional requirements, and the clever ways engineers tackle their biggest challenges.
And we've got a lot of ground to cover, but we're going to approach this like chapters in an amazing tech book. We'll really dig into each system, exploring every detail of one before we even begin to think about the next. This ensures a focused and thorough understanding, allowing you to gain some serious insights quickly but thoroughly. First up, let's lace up our virtual running shoes and take a deep dive into Strava. For those who might not know, Strava is that incredibly popular fitness tracking application. It lets users record and share their physical activities, especially running and cycling, with their network. It's all about detailed analytics on performance and routes, plus those social interactions that keep us motivated to hit the road or trail.
Indeed. And while Strava supports a whole wide array of activities, swimming, hiking, you name it, our primary focus today will be on running and cycling. This just helps us streamline the core design concepts and concentrate on the most common use cases. #1, functional requirements.
So when we think about what Strava must do, what are those absolute core capabilities, the non-negotiables that users would expect from day one? Where do we even begin?
Well, to start, users absolutely need to be able to initiate, pause, stop, and then save their runs and rides. This is the fundamental interaction. I mean, without these basic controls, the app wouldn't serve its primary purpose, right?
Right. And once an activity is underway, what kind of information do users expect to see right there on their screen?
So while an activity is in progress, users expect to see real-time data. This includes their current route on a map, the distance they've covered so far, and the elapsed time since they started. Then once they're done with their activity and it's saved, they should be able to view detailed information about their own completed activities. Things like average pace, elevation gain, the full route map. And then crucially, they also want to see what their friends have been up to in viewing their friends' activities to stay connected and motivated.
Now, to keep our design discussion focused, we're intentionally drawing a line here and leaving out some features for this deep dive. Can you clarify what's below the line for now? What aren't we tackling today?
Absolutely. Features like adding or deleting friends, which, involve complex social graph management, those are out of scope. Similarly, the entire authentication and authorization system, how users log in, manage accounts, verify identity, that's a whole separate complex topic we won't cover. Yeah. Even social engagement features like commenting on or liking friends' runs are below the line for this specific design discussion. This lets us really home in on the core tracking and data management challenges. #2, non-functional requirements.
Okay, so we've sketched out the basics of what Strava does, but the real magic and the real engineering challenge comes when we ask, how well does it need to do it? How do we ensure it's always ready, always accurate, and can handle millions of us hitting the pavement at once? That's where non-functional requirements come in.
Precisely. These are the critical qualities that define the system's performance and reliability. First and foremost, high availability is paramount. We want our app to be always accessible, always ready for a user to start a new activity. Even if that means slight, acceptable compromises on immediate consistency. Think of it as prioritizing availability much greater than consistency. A user starting a run is more important than every single friend seeing their very first GPS point instantly.
Right. And let's be real, athletes go everywhere. They run on remote trails, cycle through areas with spotty cell service, so the application has to function seamlessly in remote areas, even without network connectivity. That's huge. Plus, while you're out there actively tracking, you need accurate, up-to-date local statistics during your run or ride. No waiting for a server update to tell you your current pace or distance, right?
Exactly. And finally, the system needs to be robust enough to scale significantly. Our target for this design is to support an impressive 10 million concurrent activities. This isn't just about total users, but users actively recording at the same time. Now, while critical in a real product, areas like data privacy compliance, GDPR regulations, advanced security measures, those are out of scope for this particular design discussion. This allows us to focus intensely on the core scaling and availability challenges of the tracking and viewing features. #3. capacity estimation. Right, so while our initial requirements didn't explicitly list a capacity estimation section, that goal to scale to 10 million concurrent activities immediately gives us crucial figures to work from. We're potentially looking at, say, 100 million daily active users. And let's assume each of those users does at least one activity per day. That translates to roughly 100 million new activities being recorded daily, or about 36.5 billion activities over the course of a year.
Wow, 36.5 billion activities annually. That's a staggering number. But when we think about storing all that, the basic metadata for each activity, things like status, user ID, start 10 times, that's pretty light, maybe around 100 bytes per activity. But here's where it gets really interesting and where the bulk of the data lies: the route data. If an average activity is, say, 30 minutes long, and we record GPS coordinates every 3 seconds for precise tracking, that's approximately 600 individual points per activity. Each of those points needs latitude, longitude, and a timestamp that works out to about 24 bytes per point. So if you multiply that by 600 points, you're looking at around 15 kilobytes of data per activity just for the route. That adds up fast.
It really does. So if we take that 15 kilobytes per activity and multiply it by our estimated 36.5 billion activities annually, the total storage requirement is approximately 547.5 terabytes of data each year. Now, while this is certainly a substantial amount of data, it's definitely manageable for a well-designed system leveraging modern storage solutions. And we'll explore that further as we dive into scaling strategies. Hashtag 4. Core entities.
Okay, now, before we start thinking about servers and databases and all that, what are the fundamental pieces of information, the nouns, if you will, that our Strava system needs to keep track of to make all those functional requirements possible? We're not getting into every tiny detail yet, just identifying the big building blocks that will shape our API design.
Right. To effectively meet our functional requirements, we'll identify 4 core entities. These represent the fundamental data within our system. First, user. This entity simply represents a person using the Strava application. It holds basic profile info, settings, that kind of thing. Second, activity. This is the central entity, representing an individual run or ride. It includes key details like the type, run or ride, start 10 times, the raw route data, the sequence of GPS coordinates, total distance, duration. Third, route. While the route data could technically be embedded directly within the activity entity for clarity and maybe future flexibility, we'll define route as a distinct collection of GPS coordinates, along with their associated timestamps, recorded during an activity. And finally, friend. Even though managing friends, like adding or deleting, is out of scope for this design discussion, the concept of a friend is still necessary. It's crucial for enabling that core sharing functionality, allowing you to see what your connections are up to.
Got it. And in a real-world design session, you typically just list these and quickly talk them through, right? Just make sure everyone's on the same page about the basic data components.
Exactly. Quick alignment before moving on. Hashtag 5, API or system interface.
Now that we know what our system needs to store, how does our mobile app actually talk to our backend services? We need to define the application programming interfaces, the APIs. Our goal here is to go through each core functional requirement and map out the necessary API endpoints. Sometimes it's a direct one-to-one mapping. Sometimes, like you said, a single endpoint can cleverly serve multiple needs.
Let's start with the very first step a user takes, creating a new activity. For this, we'll implement a ppostinactivities endpoint. The request body would simply specify the type of activity, say run or ride. Upon successful creation, this endpoint returns the newly created activity object back to the client.
Okay. And to update an activity state, like when a user starts a run, pauses it, or resumes?
For that, we'd use a PACH activities.activity8 endpoint. Here, you'd send the updated state like started or paused in the request body.
And the use of PACH here is quite insightful, right? Because it means we only send the specific fields that are being updated. Makes it more efficient than a PUT, which usually requires sending the whole resource back.
That's a great observation. And while for many initial system design interviews, PUT and PACH are often treated similarly, understanding that nuance of KCH for partial updates definitely shows a deeper grasp. Moving on, for continuously tracking the activity data itself, like recording the route and distance, we'll use the POST activities.activityIDROTS endpoint. As the client app gets new GPS coordinates, it sends a location object containing coordinates and a timestamp to this endpoint. The endpoint then updates the activity in the backend and returns the updated activity object.
And for sharing activities with friends once they're completed, how does that work?
Instead of needing a separate endpoint just for sharing, we can cleverly integrate that into our existing PPCH activities by activity ID endpoint. When an activity state is updated to complete, that status change automatically triggers the sharing logic in the backend, makes the activity visible to friends. Pretty neat.
Yeah, simplifies things. And for viewing activities, you mentioned two endpoints.
Right, two distinct endpoints for different user flows. First, to get a list of activities, maybe for a feed or a profile page, we have get_eactivities.mode, user friends and page. This endpoint is designed to return a partial type, meaning it only sends back a subset of fields to limit network data, making that initial list load really fast. Then, when a user clicks on a specific activity to see all the details, a second request, get_tactivities.activityID, retrieve the full activity details for just that one activity. ###6. Optional data flow. The overarching data flow for Strava, how information moves around. It'll become much clearer as we walk through the high-level design. But at a fundamental level, you can understand that data generally flows from the client app, your phone, to our activity service on the back end. That service then interacts with our database for storage and retrieval. And the flow reverses when information is pulled from the database, goes through the activity service, and gets sent back to the client app. #7. High-level design.
Okay, now let's get into the nuts and bolts of the high-level design. When you're tackling a system design problem, especially if it's a complex one you haven't seen before, the best strategy is often to start with the simplest possible system that meets the core functional requirements. Then, from that baseline, we can layer on the complexity needed for those non-functional needs, like scaling and offline support during our deeper dives.
It's definitely a nuanced balance. If you happen to have a sophisticated, optimized solution already in mind, it's perfectly fine to present it early. But you should probably avoid going too deep into those complex optimizations prematurely. You don't want to run out of time before you've even addressed all the fundamental core requirements. #tag 7.1. Users should be able to start, pause, stop, and save their runs and rides.
Okay, for the fundamental actions. Starting, pausing, stopping, saving. We'll begin with a very basic client-server architecture. This setup involves three main pieces: a client app where users interact on their phone, an activity service on our backend handling requests, and a database to store activity info like route, distance, time. Simple enough.
Exactly. The sequence is straightforward. User hits start activity, client app sends a POST to activities. The activity service creates that entry in the database, sends the activity object back to the client. Confirmation. If the user pauses or resumes, a PTCH request with the updated state goes to activities.activityID. Activity service updates the database.
And finally, save activity triggers another PyTCH request, setting state to complete. Done.
Right. But here's a really interesting design detail to consider. How do you accurately handle the total activity time when a user pauses and resumes multiple times? A naive approach, just subtracting start timestamp from current time at the end, that would be inaccurate. It doesn't account for the breaks. Instead, a more robust solution is to maintain time via a log of status in timestamp pairs. For example, your log might look like status, started, timestamp, T0, status, paused, timestamp, T1, status, resumed, timestamp, T, status, stopped, timestamp, T3. When the activity ends, the activity service sums the durations only between started and paused or stopped events. It excludes time spent paused. This granular logging also cleverly allows for future features like showing active time versus total elapsed time. #tag 7.2. While running or cycling, users should be able to view activity data, including route, distance, and time.
Okay, so once an activity is in progress, how do users see their route, distance, and time updates right there on their screen, almost in real time? What's the most crucial part of making that experience feel accurate and immediate?
The most crucial part is accurately tracking the distance and the user's route as they move. We do this by continuously recording the user's GPS coordinates at constant intervals, maybe every 2 seconds for a bike ride or 5 seconds for a run. That granularity ensures precision.
And how exactly do we capture those coordinates from the user's device?
We leverage the powerful built-in GPS capabilities of modern smartphones. For iOS, we use Apple's core location framework, calling methods like CL Location Manager and Start Updating Location. On Android, it's Google Location Services API using Fuse Location Provider Client and Request Location Updates. Once the client app captures these new coordinates, it then sends them to our POST activities.activityIDROTS endpoint on the backend.
And what happens on the server side when those new coordinates arrive?
When the activity service receives these new coordinates, it updates the route table in our database, persisting the coordinates and their timestamp. Critically, it also calculates the distance between the new point and the previous point using the Haberstein formula. That's essential for accurately measuring distances on a curved surface like Earth, ensuring our distance tracking is precise. Now, it's worth noting here, this initial design sends updates to the server while the activity is in progress. But As alert listeners might realize, much of this logic recording points, calculating distance could initially be handled entirely locally on the client device. This is a significant optimization we'll definitely get into during our deep dives. It's often overlooked initially, but has a massive impact. Hashtag 7.3. Users should be able to view details about their own completed activities as well as the activities of their friends.
Okay, once an activity is completed and saved, it's already sitting in our database, set to complete. So when a user wants to view their own past activities or check out what their friends have done, how does the system retrieve and present that?
Right, since the data is already stored, viewing completed activities is mostly about querying that database efficiently. We simply filter for activities with the complete state. Then we apply another filter based on the user's selection, mode user for their own, or mode friends for their friends. To illustrate with SQL, a query might look like select from activities where state is complete. Then, for user activities, add where user_id. For friends, use a subquery like where user_id. Select friended from friends where user_id users.user_id, and you'd use limit and offset for pagination naturally. Our friends table would need user_id and friended columns with bidirectional entries. If A is friends with B, you have AB and BA. Making user_id the primary key there ensures efficient querying for users' connections.
And for actually displaying these activities, it's a two-step thing.
Typically, yes. The initial GET activities request gives the client that basic list, just IDs, core info, for a quick overview. When you click on one, a second GET activity ID request fetches the full details. And to show that cool map with the route, we combine the stored GPS points with a mapping service API, like Google Maps, which draws the line connecting the points. Visualizes the path. #8. Deep dives. Okay, at this point we have a basic functional system for Strava. It tracks, stores, displays. But to truly meet our non-functional requirements, especially high availability and scalability, and build a robust real-world platform, there are several areas we need to explore in much more detail. This list isn't exhaustive, but it covers some critical considerations that will significantly shape our final design. #8.1. How can we support tracking activities while offline?
This is a massive challenge for athletes, right? Many people work out in remote areas, no network, but they still want to track their activities accurately. How does this real-world scenario fundamentally reshape our initial system design?
This leads to a critical realization, a core insight. If we don't need real-time sharing during the activity, we can shift the primary responsibility for recording activity data locally onto the user's device. We only need to sync that data back to the server once the activity completes, or when the user is back online with a stable connection. This single design decision immediately solves several problems. It removes network reliability as a client-side concern during the activity. It saves significant network bandwidth, no pinging the server every few seconds. And it makes showing accurate, up-to-date local data to the user much easier, since it all happens synchronously on their device.
That's a powerful shift. It really highlights the modern smartphone as an active participant in system design. They have powerful sensors, memory, processing power, local storage. Many candidates overlook this, focusing only on the server. But for apps like Strava, the client is critical. A smart client.
Exactly. In practice, the process would look like this. We still use on-device location services to record GPS coordinates. This event data is stored locally in an in-memory buffer, an array of coordinates and timestamps. To prevent data loss from, say, a device shutdown or battery drain, we periodically persist this buffer to the device's local storage, maybe every 10 seconds. For iOS, that might be core data or user defaults. For Android, room database or shared preferences. When the app reopens or resumes, it loads any saved data from local storage, picking up where it left off. Once the activity is complete and the device is online, all accumulated data is sent to the server in a single request, possibly chunked for very long activities. After the server confirms successful receipt, the local buffer is deleted. This means, worst case, maybe 10 seconds of data loss, but we have to balance that frequency with battery life.
And for really, really large data sets on the device, would a simple key value store always cut it?
That's a good point. For truly massive data sets, a local SQLite database, like Room on Android, might be more appropriate than simpler key value stores. Though diving deep into those specifics often falls more into mobile system design rather than broad system architecture. What's really remarkable is that even after this deep dive into offline tracking, our backend fundamentally remains a simple client-server architecture. Why? Because we've offloaded so much of that continuous write load, those constant GPS updates to the client. It greatly simplifies our backend's job. There's no significant read-write skew across different paths, forcing us into separate microservices for scaling. At least not yet. Hashtag data point two. How can we scale to support 10 million concurrent activities?
Now let's talk scaling. Remember that offline tracking optimization? It makes backend scaling a lot easier, doesn't it? We've cut down backend requests for GPS updates by maybe 100x because data only gets sent once the activity is complete. Our engineering and finance teams would be thrilled.
Indeed, it's a huge win for efficiency. However, even with that optimization, we still have potential bottlenecks, primarily our database. We're looking at roughly 100 million daily active users, 100 million new activities daily, 36.5 billion activities per year. Storing this, considering metadata and the 15 KB route data, is around 547.5 terabytes annually. Large, but manageable with the right strategies. We can handle this through several common, robust strategies. First, sharding. Splitting data across multiple database instances. A good sharding key could be activity completion time, as most queries target recent activities. Distributes load. Second, data tiering. Move older, less frequently accessed data to cheaper storage. Hot data, recent, stays fast. Warm, 3-12 months, moves to slower, cheaper. Cold, 1 year, goes to archival like S3. Cost effective. Third, caching. We can introduce it later if needed for frequently queried things like popular segments or leaderboards, but it's not a priority initially as read throughput for individual activities is relatively low.
That makes sense. Speaking of databases, what kind? Relational, NoSQL, does it really matter here?
Here's a powerful insight, maybe a hot take. For this particular problem, the specific type of database often doesn't matter as much as the strategy. It's a large but manageable amount of data, no extreme read-write needs. Data is relational, but not overly complex. Realistically, any popular, robust, major relational database, Postgres, MySQL, Distributed SQL, would work great. The scaling comes from how you shard and tier, not necessarily the database's core type, and for the activity service itself. Given the low read-write throughput thanks to client-side optimization, there's no strong immediate reason to break it into microservices. When we eventually hit limits, memory, CPU, network, we simply scale horizontally. Add more instances behind a load balancer. Hashtag 8.3. How can we support real-time sharing of activities with friends?
Okay, common follow-up. What if friends want to follow along with activities in real time? Imagine seeing your buddy's stats and route update live mid-run. This definitely shifts our design closer to complex real-time systems like Facebook Live comments or WhatsApp. How do we approach that?
Right. To enable this, we would need to reintroduce periodic server updates during activities. The athlete's device sends location updates every 2 to 5 seconds. Server persists these, broadcasts them to subscribed friends. Now, your first thought might be WebSockets. And you wouldn't be entirely wrong. You could use WebSockets or Server-Sent Events, SSE though. I'd argue it's often over-engineering the problem here. There are two key insights that favor a simpler polling mechanism, even for real time. One, updates are predictable. Unlike chat, we know the next update is coming in 2 to 5 seconds. This predictability allows efficient polling intervals. Two, real-time precision isn't critical. Friends don't need the second info. A slight delay of a few seconds is perfectly acceptable, doesn't significantly impact the experience. So informed by this, Friends clients can simply periodically request updates at roughly the same interval the athlete sends them, maybe offset by a few seconds for latency. Keeps the design simpler.
That's a clever trade-off, prioritizing simplicity. But to make that live tracking feel even smoother on the viewer's screen, especially with network delays, what else could we do?
To make watching a live activity feel smoother, we can implement a smart buffering system on the client side. This means intentionally lagging the displayed location data by 1 or 2 update intervals, say 5 to 10 seconds. By buffering the incoming location data, we create a much smoother, more continuous animation of the athlete's movement. It eliminates those jarring jumps you might see with true real-time updates, making the athlete appear in constant motion like a live stream. It sacrifices absolute real-time accuracy for a few seconds, but drastically improves the visual experience and compensates for network latency. Hashtag 8.4. How can we expose a leaderboard of top athletes?
Another common feature for a fitness app like Strava, a leaderboard. Top athletes filtered by activity type, distance, country, city. How do we efficiently generate that?
Okay. The simplest, most naive approach, a direct database query. Something like select u.name, suma.distance, from activities to join users, ugroup by user or order by total distance DSC. This aggregates all activities by user. The challenge, it's incredibly slow. Running aggregations over billions of activities for every request. High latency, massive database load. Doesn't handle dynamic ranking changes well either.
So direct querying is out. What's a better, maybe intermediate approach?
We could optimize with periodic aggregation. Create a separate, smaller leaderboard table storing pre-calculated totals for each user. A background job runs regularly, maybe daily, maybe hourly, updating these aggregates from new activities. The leaderboard query then becomes a simple, fast select from this pre-aggregated table, much less load. But while faster, this introduces eventual consistency. The leaderboard won't reflect real-time changes immediately, can be confusing. And finding the optimal update frequency is tricky. Too often strains resources. Too infrequent, data is stale. For a more scalable and real-time solution, we leverage Redis, that fast in-memory store. We use Redis sorted sets. User IDs are members, total distances are scores. When a new activity is logged, we just increment the user score in the sorted set using Zine and CRBY. Querying the top n members from a sorted set in Redis is extremely efficient. O log n, or OM plus log n. Very fast.
Okay, sounds great for global, but what about filtering by country, by time range, like a weekly leaderboard?
Good question. For country filtering, we extend the concept. Create separate sorted sets for each country, like leaderboard.run.usa. When an activity logs, update both the global and the relevant country set using redis.zad or cncrby. For time range filtering, it's more sophisticated. Combine Redis sorted sets and hashes. Store each activity ID in a sorted set, activities.timestamps, with its timestamp as the score. Then, a separate hash, activity.activity, stores user ID and distance. To query a time range, use rangeByScore on activities.timestamps to get activity IDs in the range. Then for each ID, get user ID and distance from the hash, aggregate distances by user ID and memory, and finally sort. We can cache these results with a short TTL to balance freshness and load. The main challenge is with Redis, maintaining consistency between Redis and our primary database. Need robust mechanisms for failures and retries. Also, Redis memory limits. Storing every possible leaderboard combination could consume significant memory. A caching strategy might be needed. Only frequently accessed leaderboards stay hot in Redis, less common ones calculated on demand.
All right, shifting gears entirely now. From fitness tracking to fundamental infrastructure, we're diving into the essential concept of a distributed cache. You've probably heard of caching, but distributed adds a whole new layer of complexity and also amazing power. So at its core, what is a distributed cache?
Right. A distributed cache is a system that stores data, typically as key-value pairs, primarily in memory. But crucially, it spans across multiple machines in a network, forming a single logical caching layer. Unlike a single node cache, limited by one machine's resources, a distributed cache scales horizontally by adding more nodes. The entire cache cluster works together to partition and replicate data, ensuring high availability and fault tolerance even if individual nodes fail. It's really a foundational building block for so many high-performance systems. Dramatically speeds up data access, reduces load on primary databases, ####1 functional requirements. For a distributed cache, the core functional requirements are intentionally straightforward. They reflect what any good cache needs to do. Users must be able to set store a key value pair, get, retrieve a key value pair, and delete a key value pair. Beyond basic storage, a critical requirement is configuring an expiration time, or time to live, TTL, for these pairs. Ensures data freshness.
And when the cache gets full, because memory isn't infinite, we need a way to decide what to remove. For this design, we're implementing least recently used, or LRU. What does that mean in practice?
It means the items that haven't been accessed in the longest time get evicted first. The assumption is they're less likely to be needed again soon. Now, while we chose LRU here, it's always good practice to confirm with an interviewer. Other policies exist. LFU, least frequently used. FIFO, first in, first out. The choice depends on access patterns.
And just to be clear on scope, what are we not covering in this cache design?
For now, we're intentionally leaving out the ability for users to configure the overall cache size itself. That's usually a system-level config, so that's below the line for this discussion. Allows us to focus on core behaviors and distributed aspects. #2, non-functional requirements.
When designing a cache, how well it performs is often paramount, isn't it? What are the key non-functional requirements that will really challenge our design for distributed cache?
Indeed. Scale and performance are paramount. Our assumed scale for this discussion is demanding. Store up to 1 terabyte of data and handle a peak of 100,000 requests per second. These targets dictate many of our design choices.
So with that scale in mind, what are our performance and reliability goals?
Critically, the system must be highly available. It should stay operational even if nodes fail. We can accept eventual consistency for reads, but it needs to be accessible. For operations, we target very low latency, under 10 milliseconds for both get and set. And of course, it needs to be inherently scalable to support that 1 TB data and 100K requests per second throughput. It's important to clarify what we're not building. We're leaving out durability, persistence across restarts. We're not aiming for strong consistency guarantees, no complex querying beyond key value, no transactions. These are often trade-offs for cache performance. Confirming these assumptions with an interviewer is crucial, as different use cases might prioritize differently. Hashtag take and tag 3, kappa D estimation. Okay, given our requirements. 1 TB data, 100K request sec. We need to estimate the number of cache nodes. Let's assume a single cache host can handle, say, 20,000 requests per second. For throughput, that means 100,000 RPS, 20,000 RPS, so it equals 5 nodes. Adding a buffer for spikes and failures, we'd plan for around 8 nodes to meet throughput needs.
Okay, 8 nodes for throughput. But what about the 1 terabyte of data? How many nodes does that translate to?
Right now for storage. A typical AWS instance with 32 GB RAM might reliably use about 24 GB for cache data after OS overhead and safety margin. So to store 1 TB, 20.4 GB, we'd need one 24 GB, 24 GB POO node, which is approximately 43 nodes just for storage. Add some buffer for growth, maybe uneven distribution, we're looking at about 50 nodes. Since our storage calculation, 50 nodes, significantly exceeds the throughput calculation, 8 nodes, we provision based on storage. This larger node count actually gives us plenty of headroom for throughput anyway. These are rough estimates, of course, but for our purposes, we'll plan for a cluster of 50 nodes. Vital first step. Hashtag FA4 entities.
This section is almost a no-brainer for a cache, which is great. Means we can breeze through it. What are the fundamental things our cache stores? Its simplest core entities.
The core entities are exactly what a cache stores. Keys and values. In essence, the data we need to persist in memory, retrieves, manage. It consists simply of these keys and their associated values. Everything else is built around managing these pairs efficiently.
Right. In a real interview, you'd spend very little time here. Just mention it. Move on quickly to the more challenging parts.
Precisely. Hashtag tag 5, API or system interface. Our functional requirements dictate 3 primary operations: set, get, delete. These translate directly into our API endpoints, providing a clear interface for clients. Quite straightforward by design.
So concretely, how would a client interact via HTTP?
To set a key value pair, post.key, value in the body. To get a value, gkey returns the value. To delete an entry, delete.key. Simple, intuitive. And this highlights an important skill, identifying where to spend your time. These API definitions are auxiliary to the core distributed systems challenges, so move through them quickly to focus on more complex areas like distribution and scaling. Hashtag tag 6. Optional data flow, the precise data flow for our cache operations. That'll be explained within our high-level design. Essentially, client requests come into our cache instances. They perform operations on stored key value pairs, return responses. Hashtag tag shtetl 7, high-level design.
Okay, let's start building our cache from the ground up, beginning with a minimum viable product. No fancy distributed stuff yet, just a single node cache handling gets, sets, deletes. Hashtag 7.1. Users should be able to set, get, and delete key value pairs.
At its fundamental core, a cache is simply a hash table. Every modern language has one: Python's dict, Java's hash map, Go's map. They're ideal because they provide 0.1 average time complexity for lookups and inserts. Incredibly fast.
So conceptually just a mapping, key to value.
Exactly. This entire cache instance can run on a single server. API request comes in, parse it, call the right method, get, set, delete on our in-memory hash table. Now, this isn't production ready for real traffic, it would fall over, but it's a solid functional foundation. Hashtag 7.2. Users should be able to configure the expiration time for key value pairs.
Next up, expiration, or time to live, TTL. Critical for efficiency and freshness. How do we store a timestamp with each value and handle expired entries? And crucially, how do we clean them up automatically?
To achieve TTL, instead of just storing raw values, we now store value expiry timestamp tuples in our hash table. When get is called, the cache first checks if current time expiry timestamp. If yes, key is expired. Remove it, return null. The set method takes an optional parameter to calculate this expired timestamp on insertion. This keeps the cache fresh, prevents stale data.
But here's a problem. If expired keys only get cleaned up when they're accessed, what happens to entries nobody requests anymore? Our cache could fill up with dead entries, wasting memory. Inefficient.
That's a very keen observation, a real challenge. To address this, we introduce a background process, often called a janitor or a victor. This cleanup function periodically scans the cache for expired entries and proactively removes them. Frees up memory. Can run on a schedule every minute, or when memory pressure gets high. There's a trade-off. More frequent scans use more CTU, but improve memory efficiency. Less frequent saves CPU, but holds more expired data. Hashtag tag 7.3. Data should be evicted according to LRU policy.
Okay, what happens when the cache inevitably gets full? We need an eviction policy. We're using least recently used, LRU. What exactly does that mean, and how do we implement it efficiently? Tracking recently used seems tricky.
That's the central challenge. Find items quickly. O1, Andy track access order. A hash table gives speed, no order. A list gives order, slow lookups. The elegant solution, a classic pattern. Combine both. A hash table for O1 lookups and a doubly linked list to maintain precise access order.
How does that combination work in practice when an item is added or accessed?
When we add or access an item, create a node. Key, value, expiry. Add an entry to the hash table mapping the key to this node. Insert the node at the very front head of the doubly linked list. Head is most recently used. If we're now at capacity, remove the item at the tail, least recently used, from both the hash table and the linked list. The doubly linked list ensures head, most recent, tail, least recent. When an existing item is accessed, O1, hash lookup finds the node. O1, removal from its current list position. O1, move to the front. This keeps frequently accessed items fresh, safe from eviction. All core operations get, set, eviction remain O1 on average. Incredibly performant.
So even with expiration and LRU, it stays blazingly fast.
Absolutely. Though remember, these are simplified examples. Production code needs thread safety, error handling, monitoring, optimizations. Hashtag tag 8. Deep dives. So far, we've built a robust single node cache, handles basics, expiration, LRU. But to meet our non-functional requirements, 1 TB data, 100K request sec, we need to turn this into a distributed system. This is where the real system design challenges and the interesting solutions emerge.
And this is where things get really flexible too. Interviewers will often jump in with questions here, so you need to be ready to pivot. Hashtag 8.1. How do we ensure our cache is highly available and fault tolerant? Our single node is great, but what if it goes down? In production, we need our cache to stay available even when a node fails. The big challenge here is data replication having multiple copies across different nodes.
This immediately brings up critical questions. How many copies? Which nodes store them? How do we keep them synchronized? What happens when nodes fail or can't communicate? These patterns are fundamental to any highly available distributed system. Let's consider approaches. Synchronous replication, simplest idea. Write comes in, update all replicas simultaneously. Only acknowledge success once all replicas confirm. Straightforward, guarantees strong consistency, but heavily impacts write latency and availability if any replica is slow or down. Preferred for strong consistency, which isn't our primary NFR for the cache.
Right, so for our cache, where availability and performance are key, this sounds like a tough fit. More replicas mean compounding problems, hard to scale horizontally.
It's exactly. For a cache where some staleness is okay, asynchronous replication is usually much better. One primary copy updated immediately. Changes propagated to replicas asynchronously in the background. Write confirmed once the primary acknowledges. Aligns perfectly with eventual consistency. Advantages. Better write performance. Higher availability. Writes proceed even if replicas are down. Better horizontal scaling. Natural fit for caches where some staleness is okay. Main trade-off. Temporary data staleness on replicas. Failure recovery is more complex. Need mechanisms to resync missed updates or promote a new primary. A third, sophisticated approach. Peer-to-peer replication. Every node is equal except reads and writes. Changes spread via gossip protocols, nodes exchange state with random peers. Offers high scalability and availability, no single point of failure. Node processes write immediately, asynchronously propagates. However, is significantly more complex to implement. Conflict resolution is crucial for concurrent updates. Eventual consistency means different nodes might temporarily hold different values, need to handle multiple connections, manage conflicts.
So all these have clear trade-offs. What matters is knowing the options. Redis uses async by default, right? In an interview, it's less about the right answer, more about discussing options, pros, cons. Given our requirements, async or peer-to-peer seem like good candidates.
Exactly. Discussing the trade-offs is key. Hashtag 8.2. How do we ensure our cache is scalable?
We established single node won't cut it for 1 TB of data or 100K RPS. Need to spread that load across multiple machines. This is where scaling strategies, especially distributing data and requests intelligently, are critical.
You're right. Can't fit 1 TB efficiently on one node. Need to split or shard our key value pairs across multiple nodes. Each node holds a manageable portion, allows horizontal scaling by adding machines. While partitioning can mean splitting data within one system, sharding specifically means splitting across multiple machines. Earlier, a capacity estimation gave us node counts. Throughput needed 8 nodes, storage needed 50 nodes. We provision based on the higher requirement storage, so 50 nodes gives ample headroom for throughput.
Okay, 50 nodes. But the crucial question, how do we know which node a particular key value pair should live on? How do we route requests to the right place? Hashtag 8.3. How can we ensure an even distribution of keys across our nodes?
The elegant solution is consistent hashing. A naive approach like hash key, the n equals number of nodes, works if n is fixed. But add or remove a node, almost all keys remap. Disaster for cache hits, massive data movement.
So consistent hashing avoids that. How does it work conceptually? Minimizing remapping.
Consistent hashing maps both nodes and keys onto a circular key space like a ring. Use the consistent hash function, VG murmur hash. To find a keys node, move clockwise from the keys position on the ring until you hit the first node. That node is responsible. The beauty is, add or remove a node, only keys in that specific node's immediate range on the circle need remapping. Avoids full redistribution. Makes scaling much more efficient, less disruptive. You can see this in systems like Cassandra. Hashtag 8.4. What happens if you have a hot key that is being read from a lot?
The classic hotkey problem. Certain keys get disproportionately huge traffic viral tweet ID, flash sale product. If all that hits one shard, creates a hotspot, drags down performance for everything on that shard. Slow responses, timeouts. Need to handle hot reads and hot writes differently. Let's focus on hot reads first.
Right. Hot reads are a perfect example of scaling read challenges. Millions want the same content. Traditional caching assumptions fail if it's all on one node. Let's look at strategies. Approach 1. Scale up hardware, all nodes. Upgrade CPU, memory, network across the cluster. Straightforward, but expensive, inefficient. Only some nodes are loaded. Doesn't solve the root cause. Not sustainable. Approach 2. Dedicated hotkey cache. Create a separate, specialized cache layer just for hotkeys. Optimized hardware may be geographically distributed. Challenge, managing consistency between hot cache and main cache. Needs sophisticated monitoring to identify, promote, and demote keys. Approach 3. Read replicas, entire nodes. We mentioned this for high availability. Copying entire nodes allows distributing reads. Hotkey reads go to any replica. Challenge, significant overhead, storage, network, managing replication lag. Might be overkill if only a few keys are hot. Approach 4. Copies of hotkeys, selective. More targeted, often optimal. Instead of replicating whole nodes, selectively copy only the hotkeys. If user.123 gets hot, create user.123 tag 1, user.1233 tag 2, etc. Distribute these suffix keys across different nodes via consistent hashing. Clients randomly choose a suffix key for leads, spreading load. For writes, though, all copies must be updated.
So this is specifically for read-heavy hotkeys. If it's hot for reads and writes, this could make things worse due to consistency overhead, right?
Absolutely correct. The main challenge is keeping copies in sync, especially with write traffic. Most distributed caches are eventually consistent, which helps. There's also operational overhead, monitoring hotkeys, creating copies, managing lifecycle. Key takeaway. Show awareness of hotkeys as a critical operational concern, has specific mitigation strategies beyond just adding hardware. Hashtag 8.5. What happens if you have a hotkey that is being written to a lot? Hot writes are similar, create hotspots, but often present more complex challenges, different trade-offs. Approach 1. Write batching. Addresses hot writes by collecting multiple writes over a short time, for example, 3,100 meters, applying them as a single atomic update. Instead of 10,000 individual view update deaths, maybe consolidate into one update every 100 meters, adding 1,000 views. Drastically reduces write pressure. Challenge, balancing batch delay versus write visibility. Longer delay reduces load, but increases time until writes are visible. Complexity and failure recovery of buffered writes. So light reading consistency due to pending writes, best for metrics, counters where eventual consistency is fine. Approach 2. Key sharding. 4. Writes. Split a single hotkey into multiple subkeys distributed across nodes. Hot counter views.video123 might split into views.video123.1 through .10. Write comes in, system randomly selects one shard to update. To get total, sum values from all shards. Spreads, write load. Works for operations that can be decomposed, sums, aggregates. Primary challenge, increased complexity and latency for reads, need to aggregate from multiple shards. Trades write performance for read performance. Consistency across shards during failures is also a concern. Not suitable for operations needing strict ordering or atomicity across all updates. Hashtag 8.6. How do we ensure our cache is performant?
Our simple single-node cache was 01, blazingly fast. But scaling to dozens or hundreds of nodes changes everything. Performance isn't just the hash table anymore. It's how quickly clients find the right node, how efficiently requests are bundled, avoiding network chatter. Key performance considerations.
You've hit a crucial point. Even if nodes are fast, the network is often the bottleneck. Multiple hops, a connection setup overhead, many small requests, all add latency. Microseconds locally can become milliseconds or more over the network.
Good news is we've already touched on some solutions that help performance.
Indeed. Request batching from hot writes reduces latency by cutting client-server round trips. Amortizes network overhead. Consistent hashing from sharding also helps performance. Saves a round trip, no central routing service needed. Client calculates the node directly, reduces latency. The final crucial piece, especially for persistent use, connection pooling. Constantly tearing down, reestablishing network connections is a major time sink, resource drain. Clients should maintain a pool of open, persistent connections to cache nodes. Ensures a ready-to-use channel, eliminates expensive handshakes, drastically reduces tail latencies, P95, P99 response times that impact user experience. So, tying it all together for our final distributed cache design, each node, efficient hash table plus doubly linked list for LRU. Distributed design combines asynchronous replication, high availability, hot reads, consistent hashing, sharding routing, random suffixes write batching, hot writes, and connection pooling, minimizing network latency overhead. It's a symphony of distributed system patterns working together.
Time for our next deep dive. Let's unpack the system design behind a local delivery service, using GoPuff as our model. For those unfamiliar, GoPuff is all about rapid delivery convenience store goods, groceries, alcohol powered by hundreds of micro-distribution centers or dark stores. Think local corner store, delivered almost instantly.
Right, and the core challenge here is fascinating. Managing item availability across numerous localized distribution centers and ensuring orders can be placed without double booking. Two customers can't buy the same physical product. It's a complex blend of logistics, real-time location awareness, and consistent inventory management. Hashtag #1. Functional requirements. Our primary functional requirements are clear. First, customers need to query item availability by location. Crucial constraint. Items must be deliverable within 1 hour from a nearby DC. Availability represents combined inventory from nearby DCs. Second, customers must be able to order multiple items simultaneously in a single transaction.
To keep focus tight on those unique challenges, what are we intentionally leaving out?
We're not touching payments, driver routing algorithms, or broader search catalog APIs. Our system is strictly concerned with availability checks and atomic order placement. Also, sidestepping cancellations and returns for this discussion. This selective scope lets us drill down into aggregating inventory and ensuring strong consistency for orders. #2. Non-functional requirements.
For something like GoPuff, non-functional requirements are key, especially with that instant delivery promise. Targets for speed and reliability.
Absolutely critical. Availability requests, user searching items nearby need to be super fast, under 100 milliseconds ideally. Think e-commerce search speed. But for ordering, we need strong consistency. Two customers absolutely cannot purchase the same physical product. No double booking inventory. If there's one bag of chips left, only one person buys it.
And what kind of scale are we talking about?
Significant scale. 10,000 distribution centers, 100,000 unique items across all DCs. Order volume, substantial, estimated 10 million orders per day. For this problem, putting privacy, security, disaster recovery out of scope, though crucial in production. Focus is core availability and ordering. #3. Capacity estimation. Our NFR specified 10 million orders day. To estimate availability queries, let's make assumptions. Maybe a user views 10 pages, search, homepage, before ordering. Maybe only 5% who query availability actually convert.
So if we break that down, 10 M orders day divided by 100K seconds day times 10 pages viewed divided by 0.05 conversion, that gives us, 20,000 queries per second for availability. That's significant, demands careful thought on scalability.
Exactly, it drives many design decisions. #4.
Core entities, okay. Building blocks. Core entities, the high-level nouns. Not the full data model yet, just concepts for the API. What are they?
A crucial distinction first. Item versus inventory. Think OOP. Item is the class, UG Cheetos, what customers see in catalog. Inventory is the physical instance of that item at a specific distribution center. When a user queries Cheetos, we sum available inventory instances across relevant DCs. Other entities are more straightforward. Distribution center represents a physical location. Stores items, delivers from there. Order is a collection of specific inventory items purchased by a user, plus shipping billing info. Starting with concrete physical entities helps ensure you don't miss anything. #5. API or system interface.
Now, the API is how clients interact. Keeping it simple, avoiding complexity to save time, focus on core challenges. We only need 2 main APIs for our functional requirements.
First, availability. Get it availability. Takes lat, long location, optional keyword, page size for pagination. Returns a list of available item objects. Second, ordering. POS to order. Takes list of items, user's location, and request body. Returns an order object.
Interesting, we pass user location to both APIs. Why is that crucial?
Very important detail. Backend needs to confirm inventory is available close enough for that 1-hour delivery window. Not just in stock, but deliverable from a nearby DC. #6. Optional data flow. The precise data flow will become vividly clear as we walk through the high-level design, broadly. Availability query client sends location, System finds nearby DCs, queries inventory place, sends aggregated availability back. Order placement client sends order details, tracks system processes, atomically updates inventory, confirms order. Hashtag tag 7. High-level design.
Let's start by tackling the first functional requirement. Simplest possible system first, then layer on complexity. Hashtag tag 7.1. Customers should be able to query availability of items.
Querying availability is fundamentally a two-step process. First, find distribution centers, DCs, close enough to deliver within our 1-hour window. Limit search space. Second, once we have serviceable DCs, check their combined inventory, return availability. Both steps need to be fast. Under 100 meters latency goal.
How do we initially find nearby DCs?
Start with a simple internal API. Takes lat long, returns DCs within proximity, the schema DC table with lat long. Basic calculation. Euclidean distance, or better, Havastein formula, accounts for Earth curvature. Simple distance threshold gives as the crocolize candidates. Doesn't fully satisfy 1-hour drive time yet, but first step, we'll tackle that nuance in a deep dive. Next, check inventory of these candidate DCs. Query inventory table, quantity per item DC, and items table, product details. Assuming Postgres.join inventory with item, some quantities across identified DCs return results. While many e-commerce systems separate cataloging inventory, we'll keep together for simplicity here. Note you might add Elasticsearch later, putting it together. Availability flow. User request availability service location filters with the availability service queries nearby service for deliverable DC IDs. Add availability service queries inventory table, replicated SQL. Using those IDs, sums results, returns to client. Basic availability. Hashtag tag 7.2. Customers should be able to order items.
Last core requirement, order placement. Strong consistency vital, cannot double book. How ensure atomicity? Check inventory, record order, update inventory. Altogether, no race conditions.
Ensuring no double booking is the cornerstone. Needs locking or atomicity. Must lock inventory while checking recording so only one user holds the lock. Naive approach. Separate databases, orders inventory, lock inventory records, create order record, decrement inventory, release lock. Allows optimal stores but nasty failure modes. Crash after order create before inventory decrement. Subsequent users buy promised items. Complex failure sweeps, reversals needed. Overlapping needs deadlocks.
Sounds like a recipe for disaster in high volume. What's the robust, great solution?
The great preferred approach. Leverage asset properties of a single relational database, for example, Postgres, for both orders and inventory. Use a single transaction with serializable isolation level. Guarantees atomicity. Entire sequence, check, create, decrement, succeeds or fails as one unit. 2 users try ordering the same item simultaneously. 1 transaction fails, commit due to concurrency conflict if inventory unavailable. Simplifies immensely. Database handles locking consistency. Trade-offs. Consolidating couple scaling of inventory orders. Prevent specialized stores if needed. But for atomicity, collocating an asset store is generally preferable to complex distributed transactions. Order process. User requests order service initiates single transaction to Postgres leader. Transaction checks inventory, all items 0. Fails if out of stock. Records order updates inventory status to ordered. Creates rows and order items tables. Commits transactions. If succeeds, order return to user. Downside. If one item in multi-item order unavailable, whole order fails. Need helpful error message. Initial overall solution. 3 services. Availability orders shared nearby. Both used nearby for DCs. Single Postgres DB inventory orders partitioned by region. Availability reads from read replicas, performance, eventual consistency. Okay. Orders writes to leader, atomic transactions, strong consistency, strong foundation. Hashtag tag 8, deep dives. Okay, core system outlined, handles availability, orders consistently. Now, critical optimizations for real-world complexity. Starting with making availability lookups truly accurate and fast. Hashtag tag 8.1. Make availability lookups incorporate traffic and drive time.
Our initial check, use simple distance, as the crow flies. But that's not real delivery, right? DC might be close miles-wise, but across a river or stuck in traffic. Impossible to meet 1-hour promise. Need something more sophisticated.
Absolutely right. Simple distance is too crude. Let's explore approaches. Approach 1. Simple SQL distance. Euclidean Havastein. Starting point. Challenge. Ignores traffic, roads, multiple DCs in city. Too crude for 1-hour window. Approach 2. Periodic DC sync plus external service. DCs don't move often. Periodically, e.g. 5 minutes, sync DC lat long to nearby service memory. User queries iterate in-memory DCs, use external travel time estimation service, Google Maps API, etc., for precise travel time for each. Challenge. Far too many expensive external queries, especially for obviously distant DCs. Rate limits. Cost. Approach 3. Optimal. Prune candidates first. Still sing DC data to memory. Request comes in first. Prune candidate DCs using fixed generous radius, for example, 60 miles, optimistic 1-hour drive. Then pass only these restricted candidates to the external travel time service for final accurate estimate, includes real-time traffic. Significantly reduces expensive external calls while meeting 1-hour drive time requirement precisely. Hashtag 8.2. Make availability lookups fast and scalable.
Remember capacity estimation, 20,000 availability queries per second. Huge load on our DB if hitting directly, especially with that external service call. Clearly need to scale this read-heavy workload.
Classic scaling reads pattern. Inventory checks vastly outnumber purchases. Aggressive caching with short TTLs becomes crucial. Approach 1. Introduce Redis caching. Availability service queries, Redis first. Cache hit. Great. Return result immediately. Cache miss. Perform lookup on underlying DB and external service if needed. Then write result to cache. Set load TTL 1 minute for freshness. Challenge. Cache consistency. Order service must actively expire affected cache entries whenever it writes to inventory, invalidating stale cache data. Approach 2. Postgres read replicas and partitioning. Tolerate small inconsistency for availability. Use read replicas. Orders still go to Postgres leader. Strong consistency. Availability queries go to replicas, distributing read load. Additionally, partition inventory data by region ID. Sample first 3 zip code digits. Most queries hit only 1-2 partitions, not entire data set. Challenges. Sizing replicas for traffic. Ensuring partitioning prevents single replica overload. Hotspots. Final combined solution. Combine great solutions, Redis caching, serve most from memory. Read replicas, distribute DB reads. Partitioning, limit data scanned. Gets much more scalable solution for nearby service availability lookups. Handles 20K QPS efficiently.
For our final deep dive, we're tackling something notoriously complex, high stakes, incredibly latency sensitive, designing a scalable trading platform like Robinhood. If you've ever traded stocks, wondered how real-time prices show up, felt that rush, this one's for you. Important. Robinhood isn't an exchange itself, it's a brokerage. Routes trades via market makers, paid for order flow.
Right. Before we dive in, let's quickly define key terms. Symbol, stock abbreviation, for example, META, AAPL. Order, instruction to buy, sell. Market order, immediate purchase sale at current market price. No specific price target, just number of shares. Limit order, specifies target price, number of shares, can wait on exchange until filled or canceled. For this problem, assume Robinhood interacts with a simplified exchange, offering 2 main capabilities via API. Order processing. Synchronously place cancel orders. Press response. Trade feed. Pushes real-time trade data, symbol, price, shares, ordered to subscribers. Clarifying this external interface is crucial. Defines tools at our disposal. Hashtag 1. Functional requirements. Robinhood core functional requirements. Users must see live up to the second stock prices. Crucial for informed trading. Secondly, users need to manage orders, create market limit orders, cancel existing orders.
Given the huge feature set of trading platforms, what are we scoping out for this deep dive? Keep focus tight.
Explicitly leaving out. Trading outside market hours, handling ETFs, options, crypto, displaying real-time order book, primary emphasis. Live stock viewing, core order management lifecycle. In a real scenario, always confirm with interviewer what features they care most about. Hashtag 2. Non-functional requirements.
For a financial platform, non-functional requirements are arguably even more critical. Core targets for consistency, speed, scale.
Absolutely right. Precision, speed paramount, order management, high consistency. User places trade cancels, needs instant, accurate reflection, no discrepancies, delays, scale, high number of trades, 20M daily active users, AVG 5 trades day, thousands of symbols, significant transaction rate, latency, very low for price updates, order placement, aiming for under 200 milliseconds, constraint, minimize active clients connecting to external exchange API, connections typically expensive, rate limited.
And what NFRs are we consciously putting aside?
Things like connecting to multiple exchanges, complex trading fees, daily limits per user, robust bot protection, all critical in real world, but out of scope today. Introduce separate complexities. These really characterize the complexity beneath simple features. Hashtag 3, capacity estimation. From our NFRs, anticipate extremely high trade volume, 20 MDAU 5 trades day equals 100 million trades daily, across thousands of symbols, points to very significant transaction rate system must handle.
So not just final trades, each involves other data points?
Precisely. Each trade involves constant price updates flowing in, order creations, potential cancellations, continuous bidirectional data flow, constant updates to internal records. Scale isn't just trades, but underlying data changes supporting them. Plus, thousands of symbols, each with potential continuous price updates. Hashtag is tax 3-4. Core entities.
Before drawing boxes, let's list main entities. High-level concepts our Robinhood system deals with, lays groundwork.
Primary entities are quite straightforward. User represents user of the platform. Account info. Symbol represents specific stock asset being traded, meta. Identifying info, order, represents instruction to buy sell stock, created by user. Details of trade request.
Right. Again, in actual interview, list quickly, confirm understanding, ensure shared mental model.
Exactly. Hashtag tag 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 5. API or system interface. API is primary way users interact. Defining it early guides high-level design. Need endpoints for each functional requirement.
Let's walk through endpoints for a client app, how users get prices, manage trades.
Get symbol details live price. Get symbol.name. Return symbol data plus current price. Create order. PST order. Takes parameters like position, buy, sell, symbol, meta, price and cents, vital for financial precision, avoid floats. Num shares, returns order object, cancel order, simple delete order.id, returns success confirmation, list users orders, get T orders, returns paginated list of order objects, history. Crucially, user auth info, session token JWT, passed securely in headers, common secure pattern, not in request body. Easily manipulated. Hashtag tag 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 6. Optional data flow. The intricate interaction in data flow, especially real-time updates and order processing, will become clear as we detail the high-level design. Expect data flow, exchanges internal services by data back to client, sometimes via direct push. Hashtag tag 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 7. High-level design.
Complex system like Robinhood, build sequentially. Tackle one functional requirement at a time. Keep focused. Once functional recs satisfied, use non-functional recs to guide deeper optimizations. Hashtag 7.1. Users can see live prices of stocks. First up, live stock prices. One stock or many on dashboard, users expect real-time updates. How to deliver that efficiently.
Let's consider approaches. Approach 1. Client pulls external exchange directly. Simplest thought. Client pulls exchange for each symbol every few seconds. Challenges. Incredibly inefficient. Redundant calls from millions of clients for same data. Overwhelms exchange. Network. Slow. Meeting 200 meters SLA needs polling every 200 meters. Unreasonable. Wasteful. Rule this out. Approach 2. Client pulls internal symbol service. Step up. Client pulls internal symbol service proxy. Performs key value lookup on internal cache. Cache kept up to date by symbol price processor listening to exchange feed. Centralizes exchange connections. Reduces direct connections. However, clients still pull indiscriminately even if price hasn't changed. Wasted HTTP traffic. Slow updates dictated by polling interval. Approach 3. Optimal. Server-sent events. SSE. Optimal approach uses SSE. Persistent unidirectional connection over HTTP. Superior to WebSockets when server primarily pushes data, like price updates. Perfect example of real-time updates pattern. SSE establishes persistent connections. Servers push live price changes instantly. Handles networking efficiently. API includes pposted subscribe. Client sends list of symbols to follow. Backend sets up SSE connection. Client desk simple service server. Sends initial prices from cache, updated by symbol price processor listening to exchange. Symbol price processor also sends real-time updates to symbol service, which fans out updates to all subscribed clients via SSE. Challenges with SSE. Maintaining persistent connections. Load balancers need sticky sessions. Client stays connected to same server. Handling disconnects, reconnects gracefully. Routing user connections symbol data efficiently across symbol service instances. Needs careful thought. Deep dive topic. Hashtag 7.2. Users can manage orders for stocks.
Next, critical task. Order management. How users create market limit orders, cancel existing ones. Involves significant backend coordination with external exchange.
Again, consider approaches. Approach 1. Client directly interacts with exchange. Simplest thought. Client talks directly to exchange. Cuts backend latency. Yes, but huge number of expensive exchange clients requests from mobile devices not allowed handled. No clear reliable path for client to track order status. Client storage unreliable. Direct polling not viable scalable. Approach 2. Order service on queues for dispatch service. Better idea. Order service receives orders on queues for order dispatch service. Dispatch service proxies exchange, centralizes communication, queue prevents overload, allows elastic scaling, however, breaks down with tight 200 meters order SLA, high queue loaders, slow scale up, unacceptable delays, disastrous for quick trades cancellations. Approach 3, optimal. Direct dispatch via gateway, preferred, most performant. Order service sends orders directly to order dispatch gateway, for example, AWS NAT gateway. Ensures outbound requests to exchange seem to come from small, managed set of IPs often required. Order service runs core logic, accepts client requests, auto-scales aggressively, CPU usage, or over-provision for spikes. Needs efficiency for client and exchange interaction. Potentially batches orders.
Okay, we know how orders go out, how store track them internally so users see them via GET orders.
Need an order database. Horizontally partitioned relational DB on DG, Postgres. Sharded by user read. All updates reads for a user hit single node partition. Fast queries for users' orders. Order record contains details, status, pending, submitted, filled, canceled, critical, external ordered from exchange upon submission. To keep these orders up to date with exchange. Need a trade processor. Fleet of machines connected to Exchange. Webhook. Exchange pushes real-time trade status updates. Trade processor receives updates, efficiently updates internal order database.
And how that trade processor actually reflects updates efficiently sounds tricky. Let's dive into that next. ############################################################################################################################################################################################################################################################################################################################################################################################### real-time demands, stringent consistency. Hashtag tag 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 8.1. How can the system scale up live price updates?
Millions of users subscribing to thousands of stocks. How efficiently route those price updates to the correct symbol servers connected to specific users who care? Massive fan-out problem. Classic fan-out challenge. Leverage Redis PubSub for elegance. Symbol price processor. Listens to exchange feed. Publishes price updates to Redis channels. One per symbol, e.g. prices.aapl. Each symbol server maintains dynamic subscriptions to Redis channels for symbols its connected clients care about. Price update published to Redis, subscribe, symbol service servers, receive it. Fan-out update via SSE to all their connected clients subscribe to that symbol. Workflow. User subscribes to symbol via symbol service server tracks. Symbol vs user connections, mapping, ensures active subscription to corresponding Redis channel. Symbol price processor publishes update to Redis symbol service server receives, pushes to relevant user connections. User unsubscribes, disconnects, server removes from subscribes from Redis channel if no more users interested on that server. Self-regulating system evenly distributes load, efficiently propagates updates. Hashtag 822. How does the system track order updates?
Earlier, trade processor gets updates from exchange. Tricky part. How know which internal order, partitioned by user id, corresponds to an external ordered from exchange? No easy lookup in order table by external ordered.
Needs a separate dedicated key value store, highly optimized for fast key lookup, v.g. RocksDB, maps external ordered from exchange, internal ordered usered air, populated by order service after successful submission to exchange when external ordered received. Trade processor workflow becomes efficient, receives trade update with external ordered, quickly queries new KV store, age is ordered and user did. With user add, identifies correct partition in order database. With ordered, quickly looks up and updates specific order details, reflects trade accurately. Hashtag 8.3. How does the system manage order consistency? Order consistency, absolutely critical in finance. Ensure orders managed consistently internally and on external exchange. Fault tolerance is key. Order database. Horizontally partition relational DB, Postgres, sharded by user. Updates reads for a user hit single node. Simplifies consistency for individual users.
Let's break down order creation workflow step by step. Potential failure points, consistency measures.
Certainly. Step 1, stores pending internally. First action. Store order in order database, status pending. Crucial failsafe. If system fails before submitting to exchange, have record of intent. If this DB write fails, respond failure to client. Step 2, submit to exchange. Synchronously submit order. Wait for confirmation, get external order it. If this fails, network, exchange rejection. Mark internal order failed, tell client. Step 3, update external order in status. Exchange submission success. Write external order to our KV database, RocksDB mapping. Update ordering order database status pending, submitted. If this update fails after successful exchange submission, rely on cleanup job. Background job scans outstanding pending orders, queries exchange, using client-ordered metadata sent originally. Records external ordered or marks order failed. Step 4, respond to client. Only after internal updates, respond success to client. Cancellation flow has similar fault tolerance needs. Step 1, update status to pending cancel. Allows resolving failed cancels later. If fails, respond failure to client. Step 2, submit cancellation to exchange. If fails, respond failure. Rely on cleanup process to scan pending cancel orders. Ensure cancels via retrieves reconciliation. Step 3, record cancel status in DB. Cancellation confirmed by exchange. Record final cancel status in order database. If this final step fails. Cleanup process. Again, scans pending cancel, update status appropriately even if already canceled on exchange. This detailed analysis confirms absolute necessity for robust, idempotent cleanup background process. Constantly scans internal state, reconciles with external exchange, ensures order state consistent despite failures. Ensures eventual consistency despite distributed operations. Vital for financial trust.
That was a lot, right? Complexity in financial systems is immense. Truthfully, we could go even deeper. Just a few more thought-provoking areas we could explore if we had more time.
For instance, excess price updates. How handle overwhelming flood of updates for volatile stocks?
How's that?
Avoid swamping service clients. Or limiting exchange correspondence. Beyond what we covered, other ways to batch orders, intelligently manage interaction, limit expensive calls while serving users. What about live order updates? How push real-time order status updates, limit order filled directly to user app instantly, and historical price portfolio value data. We focused on live, how show historical trends, track portfolio value over time, aggregating vast historical data.
Lecture.
Hashtag outro about them.
Wow, what an incredible journey through the intricate world of system design. From tracking your runs with Strava, ensuring lightning-fast data with distributed cache, getting snacks delivered by GoPuff, even trading stocks on Robinhood, you've seen the incredible thought, the engineering that goes into making these seemingly simple experiences possible.
Yeah, and if we connect this to the bigger picture, you've witnessed how functional requirements lead to initial designs, how those designs get rigorously tested, optimized against non-functional needs like availability, consistency, scalability, and how common patterns, sharding, replication, caching, clever data structures are applied across remarkably diverse problems. Understanding the trade-offs, selecting the right pattern for the right problem, that's paramount for any system designer.
I truly hope you had as many aha moments as I did during this deep dive. It's truly fascinating to peer behind the curtain, see how engineers solve these incredibly complex challenges to create the seamless digital world we live in. You now have a fantastic shortcut to being well-informed about some seriously sophisticated systems.
So as you use your favorite apps today, maybe consider this. Which seemingly simple features might be hiding the most complex system design challenges beneath its surface? What stands out to you about that delicate balance between performance and consistency in the services you rely on daily?
That's all for this deep dive. Join us next time for another exploration into what makes our digital world tick. Stay curious.